The next section we want to talk about is 4.6, and it is concerning related rates. Now, we did a few problems that sort of introduced this sort of relation between things in 4.5, but this time we're looking at rates, so it's all with respect to time. Basically, what you use this for is when you have different variables, all that are functions of time, all that relate to time. And we're going to differentiate with respect to time to figure out what's going on. The biggest thing you need to remember is that if they tell you how fast something is moving, that's a derivative. Okay, remember, derivatives are instantaneous rates of change. So if they're telling you how fast something is changing, then that's a derivative with respect to time. On page 234 in your book, you have the steps all listed out and how to do this. And I expect that you're reading the sections. I expect you always are. So make sure you read those. And we'll do a couple of examples in this video. So the first example, let's go with this. A rope is attached to a pulley, which is mounted on a 15-foot tower. The end of the rope is attached to a heavily loaded cart, hence the pulley. A worker can pull in the rope at a rate of 2 feet per second. We want to know how fast is the cart approaching the tower when it is 8 feet from the tower. Okay, so the first thing we want to do is draw a picture. Pictures are going to help you label everything so that you can have an idea of what's going on. So we've got this 15-foot tower with a pulley on it and this rope, and it's attached to this cart. And there's a person here. Yes, Miss Hutcherson is not an artist. And now, the thing that you need to realize is some of these sides and things are going to be labeled as variables, and some of them are going to be labeled as standards. For example, this tower is 15 foot tall. It's not changing ever. It is 15 foot tall every single time, no matter how much rope is pulled in. The tower is 15 foot tall. We don't know how much rope is here because it's getting pulled in, so it's constantly changing. And we don't know how much space there is between the tower and the cart because it is also constantly changing. Now, when we have, here, let's call this S, since it's not a height, it's a sideways position. All right, so when we have this, what information are we given? Well, we're given that it's a 15-foot tower, which we've already labeled. A worker can pull the rope in at a rate of 2 feet per second. Well, what does that mean is changing? Right, the length. So the length is changing with respect to time. See, per second, that means with respect to time. And it's decreasing by 2 feet per second. So we make this negative because the length of the rope is decreasing by 2 feet per second because he's pulling it in. Now we want to know how fast the cart is approaching the tower. So what we're looking for is how fast this is changing, how fast the cart is approaching the tower. That's what we're looking for. And we're looking for that when it happens to be at 8 feet. It's not always at 8 feet, so you cannot label your picture with it being 8 feet. Okay, keep that in mind. Make sure you understand that. Now, what we need is an equation that relates what we know here. Well, we've got this S, and we've got this L, and we've got 15, and if you look at this, if the picture was drawn a little bit better, you would see that what we have here is a right triangle. Okay, this is a right triangle, and we've got that S squared plus 15 squared equals L squared. Pythagorean theorem. Now, one thing we need to know is we're looking at rates with respect to time, and we want to compare all those, and we want to solve for ds dt. This is what we're looking for. So how do we find that? Well, we take the derivative with respect to time. So when we take the derivative, this is a function of time. The position is changing with time, so it's a function of time. So I take its derivative, and I have to use the chain rule because I'm taking my derivative with respect to time. Then here, 15 squared, it's a constant, so the derivative is 0. And then here, again, the length of the rope is a function of time. It's changing with respect to time, so I have to use my chain rule to take that derivative. So now what I need to do is plug in all my values that I know at this time that I'm looking at, and I'll be able to solve for the one that I want, which is this ds dt. So I know what S is at this time. It's 8 foot. So I take 2 times 8, and we're going to leave our units in so that you can see the importance of the units. And we don't know what ds dt is. That's what we're solving for. And then 2 times, now this L here, we don't actually have that written down anywhere, but do we know what it is at this particular moment? Of course we do. We know what S is. We know this side is 15. So if we have 8 squared plus 15 squared, at this particular moment, we'll know what L is. And L, at this, if you solve this out, you get L is 17 feet. So we have 2 times 17 feet. And then here we know what dl dt is by times negative 2 feet per second. Okay, so now we're solving this out. So we have ds dt equals, we can multiply this. We've got, actually, you know what, let's not multiply this. Let's do this the easy way. So we've got 2 times 17 times negative 2, and that's feet squared per second. And that's all divided by 2 times 8 times feet. So these are going to cancel. And then here we're left with 4, and we're left with negative 1 there. And then the feet cancel. So we just have one of them left. So we have ds dt equals negative 17 over 4 feet per second. Now, could you have multiplied this out, of course, and divided it? That's fine. But this is just a way to kind of remind you don't have to rely on that calculator. Sometimes you can just put it out there and cancel things out, see what's going to happen. The other thing that you need to pay attention to is these units. Notice here the units, the way it works out, so that the position is changing with respect to time in feet per second, which makes perfect sense. The units actually should work out mathematically to get what you need. If they don't, then somewhere along the way you made a careless mistake or you set your problem up wrong. The units will really help you see if you've set it up properly. So make sure you include those units. All right, let's do one more. Okay, this is kind of long, so here. I'm just going to draw you a picture and read the problem, okay? An oil storage tank is built in the form of an inverted right circular cone, so it looks like this. Okay. With a height of 6 meters, so the height of the cone is always 6 meters, and a base of radius 2 meters, so this radius here is always 2 meters. Oil is pumped into the tank at a rate of 2 liters per minute. So what is that? Well, that's change in volume, right? It's pumped in. The volume is changing with respect to time, 2 liters per minute. How fast is the level of the oil rising? So we've got this oil level in here. So that's the top of the oil. How fast, if we call this height, we want to know how fast that height is rising. How fast is the height changing when the tank is filled to a height of 3 meters? So I'll read that again. An oil storage tank is built in the form of an inverted right circular cone with a height of 6 meters and a base of radius 2 meters. Oil is pumped into the tank at a rate of 2 liters per minute. How fast is the level of oil rising when the tank is filled to a height of 3 meters? Okay, now the first thing you should notice is we have a unit problem here. We're looking at height and all these distance length measurements in meters, and our volume is in liters. So we need to get that in cubic meters so that we can deal with it. So we use our dimensional analysis, unit conversion that you learned in chemistry, hopefully. We've got 2 liters in 1 minute. We know that 1 liter is 1,000 milliliters. We know that 1 milliliter is a cubic centimeter. Hopefully you know that. You should make sure you remember this conversion. That's really, really important. And then we know that, let's see, 100 times 100 cubes. So that's 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. Cubic centimeters is 1 cubic meter. So we can have 3 zeros we can take off here. So we've got 2 divided by 1,000. So this is 0.002 cubic meters per minute. This is one of those times where you really have to pay attention because the units, I'm telling you, those units, you've got to pay attention to them. No more just dropping off units because you're doing a word problem and then slapping them on at the end. That won't work. You'll get yourself all messed up. So we've got, this is our change in volume with respect to time that we're going to use because then the units all agree. Well, what have we got? Well, we know we're talking about volume, and the volume is 1/3 pi r squared h. That's the volume of a cone, but we're not really paying attention to this radius here. We don't want to have anything to do with that. We know about the height. We know about the change. We're looking for the change in height. We don't want to deal with the radius. So what we need to do is get the radius in terms of the height. How can we do that? Well, if you look at this, you've got a couple of right triangles here. You've got this big one, and then you have this one here that's the actual amount of oil. And if you notice, they are similar triangles. They share the same angles. All 3 angles are the same, so they're similar triangles. And if you recall from geometry, you can set up a ratio where we say that the height of the little triangle over the radius of the little triangle equals the height of the big triangle over the height of the other leg, I guess the radius, for the big triangle. So what this means is the radius is the height over 3. If you cross multiply and figure that all out. So now we can take this and plug it in here, and we end up with 1/3 times pi times h over 3 squared times h, which means we get pi over 27 h cubed. So now we have a volume equation. It's in all the variables we want it to be in without any extra variables that we're not dealing with, and we're ready to go. So our volume, this equals the volume. So volume, we've got d, take the derivative with respect to time. The derivative of v is dv dt. And then here we're going to use our chain rule and take the derivative of that side. So you end up with pi over 9 h squared times dh dt. Well, now we plug in what we know. dv/dt. Remember, we're using this one with the right units. And then we're looking at what happens at the particular time when the height is 3 meters. Oops, times dh/dt. So we get 0.002 meters cubed per minute equals, if we square this, we get 9 meters squared, so the 9's cancel. So we have pi meters squared times dh/dt. So we have 0.002 meters cubed per minute divided by pi meters squared equals our dh/dt. So the meters squared cancels here, so we're just left with meters per minute, which is what we want. That makes sense. The height is going to change in meters per minute. It's not an area or a volume. We just want that linear unit. And then we divide the 0.002 divided by pi, and you get approximately 6.366 times 10 to the negative fourth meters per minute. That's a terrible approximate sign, sorry. And there we have it. So the biggest thing with these, set up your equations. Remember that rates of change are derivatives with respect to time. Write down what you know, draw a picture, only labeling what you know is true all the time. Put variables in there for anything that changes. And then write down what you know, get your equations together, take those derivatives with respect to time, pay attention to your units, and solve it all out. We'll do one together in class the next time we meet. Make sure you have read this section, looked over the examples in the book, and written down any questions that you have.